Hi, HMS modelers. This is Lauren Coe from the Hydrologic Engineering Center. This video is a recording of a webinar that took place on December 3rd, 2024. In it, you will hear from three members of the HEC-HMS team, Tom Brower, myself, and Mike Bartles. In this webinar, we presented new gridded data features available in version 4.13 of HEC-HMS, including a generalized data reader functionality that allows for more flexibility in gridded data file types and new gridded parameterization features. Enjoy and happy modeling. Thanks for joining us on our first quarter FY25 HMS webinar. In just a second, myself, Lauren Coe, Tom Brower, and Mike Bartles are going to provide you all an overview of the new Generalized Data Reader capability within HMS, as well as some of the new gridded parameterization features. Along with those, we're going to sprinkle in some live demonstrations so you guys can see those features in action. But before we get into that, a little housekeeping. This webinar is being recorded, and that video is going to be posted to our website soon, most likely by the end of the week. Because of that, to minimize disruptions, we're going to keep everyone on mute, but we do ask and encourage you to put any questions in the chat as we go along. We'll have some time at the end for questions and discussion. So please type your questions in. We'll either answer them as we go along, get to them at the end, or if all else fails, we'll email you back any responses and follow up with you. With that, I'm going to turn it over to Tom to kick us off.
All right, thank you, Lauren. Good morning, everyone. So like Lauren said, we're going to go over some exciting new features that I think are mostly in HMS 4.13 beta, which is out now. And I apologize if they aren't quite there yet, but I'm pretty sure these are. I kind of lose track of where things are. But the features we'll be going over: generalized data reader, gridded parameterization. They are similar, but they're also different. And we'll just go over those today. The good news is, well, at least I think the good news is that this is a fairly demo-heavy presentation. I think you all seeing us use the new features is extremely helpful for the application. So, outline of what we're going to go over today. The first two bullet points here pertain to the generalized data reader. The last two bullet points pertain to the new gridded parameterization. So first, I'm going to demo what it looks like to use a netcdf file for precipitation and temperature boundary conditions instead of the traditional HEC DSS. And then Lauren is going to show what it looks like to use a geotiff for initializing states with gridded snowmelt as that particular application. So in both those cases, we're going to use something other than HEC DSS, and that's showing off our new generalized data reader feature. Then we're going to move on to gridded parameterization. We have a exciting new way to parameterize gridded models. Traditionally, we parameterize those with grids, and by grids I mean like rasters, in the form of an HEC DSS file. Now we can parameterize those a little more directly, so you can input a value for a grid cell. So I'm going to show that off along with Mike, who's going to show that same concept in a more advanced application, which is unstructured discretization and with 2D and Mod Clark, those kinds of things. So a lot of great stuff to see today. All right, with that, I'll kick it off. I alluded to what generalized data reader meant just a minute ago. I'll go through these bullets. So what we did is in memory in HMS, in the program, this is more of a developer thing, but I'll just explain it, is the representation for what a grid is, we abstracted that away from HEC DSS. So traditionally in memory, the grid looked a lot like the HEC DSS, to the point where in memory we're dealing with like path name parts and things like that are very DSS oriented. And what we have done is we wrote that more generally to try to accommodate input from any raster or grid data source. And the initial targets you see listed here, we wrote readers. We've maintained HEC DSS, obviously. It's not going away anytime soon. But we've also added readers through things like netcdf, a more commonly used scientific data format that's out there, as well as GeoTIFF and ASCII, which are pretty popular raster formats that include a spatial notion or a notion of where they are in space. So that's the initial implementation. And because we've generalized this in the future, should other file formats arise that we want to accommodate, we certainly can. So the what this means for you as the end user is that gridded data doesn't have to be an HEC DSS format anymore. So maybe you love DSS, maybe you hate it. Either way, you can still use it or you don't have to in the future. There are alternatives. And really what this is kind of setting up for a future where DSS isn't the only option. We want to make sure we can accommodate different data formats as the practice and the formats that are out there, they just evolve in time. So we want to be open to those as they come. All right, with that, I'm going to jump straight into a live demo. So let's do that. I'm going to pull up a project in HEC-HMS. And what I want to demonstrate for you is just boundary conditions using netcdf file format. It's relatively simple, but it's totally novel at the same time, so it's worth showing you. I'm going to start, I have my project set up, and this demo, I'm going to run a simulation that uses the traditional HEC DSS format for precipitation and temperature boundary conditions. And I'm just going to do the same exact simulation, but instead of using HEC DSS, I'm going to use netcdf. Just to show it can be done, we'll compare results at the end, make sure everything checks out. I'm going to start with Vortex though. I think a lot of you are familiar with this. In HMS, we call it the gridded data import, which is launchable from file import gridded data importer. That's a bit of a mouthful. I have it open already. That's how you would get to it if you didn't have it open. What I'm going to do, you might be familiar with this. If you are, cool. If you're not, I'll try and verbalize my steps just so you can see. But a lot of this is very traditional. We haven't changed a whole lot. I'm going to select a bunch of grid files, and those grid files contain precipitation. The data source happens to be MRMS, and yeah, pretty standard workflow. I'm going to select a variable. This gauge corrected QPE is the precipitation variable. So there's a file, and then within the file, there's kind of this inner directory, and that's what I've just selected here. I'll go to the next step. I can clip this data down to my basin. So I have a shapefile of my Punxsutawney Basin. So I'm just going to specify that I'm going to clip it to that here. Next, I'm going to reproject it into SHG. That's just good practice. HMS will reproject it if you haven't projected it, but I like to reproject my data before applying it in the program. And then I can also resample the grid cell size. I'm going to use a fairly standard 2000 meter. Doesn't have to be, but that's what I'm going to be using for this demo. And then resampling method, I'm going to use bilinear. So that's that. All right. All of that is much the same as you have done in the past. What I'm going to do differently here is I'm going to save this data, not to HEC DSS. I'm going to save it to netcdf. So I'm going to put it in this data directory on my folder. You see things kind of default to DSS still, but I can change that to netcdf. So I'm going to name my file precip.nc. NC is the extension for netcdf. And that's where I'm going to put it. So I'll let that import run. And while that's going, what I have already done is I have gone through this process for my temperature data. So right now I'm importing precip. Let me just show you what this temperature data looks like. Let me browse to that. So on the right here, this program is called Panoply. Let's go with an analogy here. So HEC DSS format is to HEC DSS view, as netcdf format is to Panoply. Hopefully you're tracking that. So Panoply is just a viewer for netcdf data. And what I have done here is I've opened this temperature.nc file in the Panoply viewer. You can see there's a temperature variable inside of this file. This temperature variable is analogous to like the DSS path name, which has like 6 parts. You're probably familiar with that. NetCDF convention has inner variables, and they just have a single name, usually like temperature as we see here. What I can also do in Panoply is I can, much like HEC-DSS view, you can view your gridded data. I'm going to do the same thing for this temperature data in Panoply. So I can just create a view. There's air temperature, and I can cycle over time steps like that so you can see the data. I can also look at the data in an array form. So this is just my gridded data for a particular time step, and I can step over time steps and see for each grid cell what it happens to be. So like I said, Panoply is just a data viewer. I just opened that up to give you an idea of what the data actually looks like. Let's go apply it in HEC-HMS now. So my precip data has imported. And as always, with gridded data in HEC-HMS, we add a what we call a grid shared data object. So I have grids. Here's my QPE grid for the HEC-DSS format. This editor looks much the same as it always has. Now, let me go. I've stubbed out a place for my netcdf data. Let me go there. This is what the editor looks like. Now you can see here, one of the things that's changed is there's now an option for netcdf. We have single record HEC-DSS, multiple record HEC-DSS, but there's now a new option for netcdf. I'll go ahead and select that option, and I can browse to my file. So it's going to be the precip.nc file. And then, like I said, the netcdf variable is analogous to a DSS path name. Let's take a look again. So here we've selected the inner path, and I'll do the same for netcdf. The variable I want to select is precipitation, so I've selected that. Now, my DSS-based compute is named September 2018. I can go ahead and compute that. And my netcdf-based compute, I already set this up, is named the same thing, but I just added an NC to the end. So let me go ahead and compute that. I just computed the simulation using netcdf boundary conditions. We can take a quick look at our outflow for both of those. These should plot on top of each other. They do, which is good. So I can take boundary conditions from either netcdf files or DSS files, get the same results. That all checks out. So that's the demo. Let's see if I can pull my slides back up. I have one summary slides here. Oh, that didn't go as planned. Let me navigate to my summary slide. All right, here we are. All right, so I just showed netcdf, HEC-DSS as a boundary condition. First of all, I'll say in our testing thus far, I have not seen any significant file size or performance differences, but the jury's still out. We're still testing things. netcdf has some more advanced compression options available. So depending on how things go, we might play around with those parameters. Those would be the major advantages, I would say, of using netcdf is to maybe, in some ways, it might be more performant. So netcdf4 is actually based on HDF5. So like I said, we haven't came up with anything conclusive yet, but we have the read availability now. So we're still out there testing both performance in terms of performance on disk, and then performances in terms of performance in memory and read times and write times and things like that. But the foundation has been set for all of those kinds of potential performance benefits. And then second note here is that really this just sets up a departure from HEC DSS format as a requirement. And like I said, HEC DSS isn't going away anytime soon, although certain people at HEC, I won't name names, might wish that. Just having to maintain that is a big burden. So the idea is that if there is other standard file formats with their own libraries that we don't have to pay the maintenance cost on, then why not try to use some of those other options? So that's kind of the idea there. All right, so I just show a gridded boundary conditions. I'm going to pass it over to Lauren, who's going to show what this looks like for what the generalized data reader affords us for initializing states.
Awesome. Thanks, Tom. Let me share my screen. Okay. Let me put it on preserve. All right. So before I get into kind of demonstrating and going over how our generalized data reader is going to work in the gridded temperature index for initializing states, I wanted to do a quick review of some of the prior enhancements that were done in gridded temperature index to get us to where we're at now. So the gridded temperature index method for modeling snowmelt, simulating snowmelt in HMS requires a variety of parameters, but the first parameters that need to be defined by the user are some way to initialize these 5 state variables, those being snow water equivalent, cold content, liquid water content, cold content ATI, and melt rate ATI. So there's some brief definitions here on the slide. There's definitely a lot more information within our user documentation, both in our user manual as well as in our tech reference manual. So I encourage you to check those out if, snow melt modeling is maybe new to you or a little foreign. But the takeaway here is that these snow states can be initialized using observed gridded data. So now let's take a look at kind of how those initialization options have evolved in HMS. So prior to version 4.12, the initialization of these 5 state variables were set as a group. So they basically were set for all of these 5 states with either the option being parameter grids, which was a DSS file, or default values, right? And so what you may have noticed by just hearing the names of those variables, likely still water equivalent is the one that stands out because it's the one that we hear about the most. It's the one that's most readily available. And often that is the grid that's most widely available. And it may be the only snow state grid that you actually have data for. So what this meant was when you wanted to use a SWE grid in the past, prior to version 4.12, you would input your observed SWE grid, but you would also need to input some type of dummy grid for the remaining state variables, right? So the user just had to be a little creative, create some kind of 0 or default value grid just to plug in to get the program to run. In version 4.12, an enhancement was made that allowed you to like granularize the methods by each state variable. So now they can be changed distinctly from each other, and you have 3 options. You still have initial grid, default value, and then a third option was added as well for a constant value that the user could input there. So with this enhancement, the best thing about it is that you can now initialize SWE with a grid, and you can keep everything else as a default without having to create these dummy grids. Or the user can actually input a constant value for those as well to initialize. Okay, so now we'll get into how the generalized data reader comes into play here. So in addition to using the DSS file to initialize those states, we now can use GeoTIFF, ASCII, or NetCDF as well. All right, so now I'll hop over to do a demo. Let's see. Okay, so in this example that we're going to demo, we're just going to kind of go through the workflow of using a GeoTIFF to initialize snow states. So this example has a simulation run for a full water year. And if we take a look at our snow initializations, we see that for this water year 2017 simulation, we have all of our initial states are using the default value. So the water year starts in October, and if we think about that, that makes sense. We don't expect there to be a big snowpack in October, so using a default value is probably a good assumption, right? A lot of those default values are 0, basically. So if we take a look at our results for this water year simulation, obviously these snow parameters have been well calibrated. We're having really good agreement throughout the water year for our snow water equivalent. And if we take a look here, we can see that if we wanted to, we could use our spatial results to export a snapshot of the snow water equivalent for a time when we do have snowpack, right? We do have snow water. We do have a non-zero start point for snow water equivalent. So let's assume that we want to initialize in mid-January of 2017. We can use our spatial results to export a geotiff and get that snapshot. So let's do that here. We can select our basin model, select SWE on spatial results. We can export these here. So we're going to export a single grid, and hopefully I can quickly get to the point we want here. I think I said noon. Okay, so that's our start date. That's our snapshot. And then for our file type, we're going to do geotiff. We'll export this. Probably have a couple already. Export. And then we have our location of our geotiff there. So if you think about kind of the use for exporting this kind of snapshot, in this case, we're just going to plug it into basically maybe what is basically like an event calibration or simulating an event. But it also has implications if you wanted to do something like stochastic storm transposition and you want it to bring some type of severe storm and apply it to a basin with certain snow states, right? And you say you want it to use that particular snow state that we saw here on January 15th. So that's kind of the other application of this. So if we go now to create our SWE grid, do new, we'll call it January 2017 TIFF. Go to our snow water equivalent grid. So on our data source, we're going to use the drop down and go to geotiff, right? Our file name, I've already had this one loaded in the data folder. That's where you should put your data, obviously. Save that. And now let's check out our basin model here. So we'll go to our snow grid and you can see that we've got all these initial states and how we're initializing them. So we've got a grid now for SWE. So we're going to change that to parameter grid and select our TIFF. We'll run that and we'll just go back here to remind ourselves of what we expect this snapshot to be, right? So I have it called out here. We're right at about 22.5 inches of snow water equivalent on January 15th, about midday. That's when our simulation starts, I think. So if we go and look at our snow melt graph, we see that we're capturing that snapshot, a non-zero start point with the geotiff we exported from spatial results. Oh, sorry, I didn't mean to stop sharing. So just to kind of review there, some of the advantages of the generalized data reader for using a geotiff versus a DSS file. A geotiff is definitely far more common as a raster file format. Also, being able to use a geotiff directly eliminates the need to convert back to a DSS to initialize these grids. That's something that we had to do, or I had to do in some of the testing. I had to take a geotiff, put it back into a DSS before that capability was there. And then finally, again, it sets up that departure that allows us to use something other than a DSS format for these initial conditions. So with that, I will pass it back to Tom to talk about some of the gridded parameterization.
All right, thank you, Lauren. I'm going to share my screen. All right, we should be up and running. So that kind of wraps up our generalized data reader content, although it kind of bleeds into some of what we're about to present. So it's not going away. You'll see it again. But we're going to shift gears a little bit into the new gridded parameterization. I'll go over some of the advantages up front. They might not make sense right away because you haven't seen it yet. But we'll start with this bulleted list and we'll get into a demo and take a look at what it actually looks like. So I'll start by saying we have new gridded global editor, so a new user interface for interacting with gridded methods. And what is nice about these new gridded global editors is they show values on a grid cell by grid cell basis. This has not been a part of the program ever before, and it's pretty exciting that you can. It seems simple once again, but it's very exciting because of what it means for model development and troubleshooting. There's a new approach called specified values, and this is where you can actually specify the value for a grid cell. So we're no longer reading it from a raster. We can just put the value in the model for each grid cell. There is still this concept of reading from a raster, and we're calling it state grids. So we can initialize like what Lauren showed, where she was initializing the SWE state from a raster. That is now known as state grid initialization, as opposed to specified values. So I'll demo that. And just one nice thing about the specified values approach is that if you do employ it in your model, and the lifetime and life cycle of your model and all of the calibration runs, you're going to do a lot less raster sampling. So what this affords us is the ability to sample values from those rasters one time, and that be that. Then you don't have to do that raster sampling anymore. All right, let me show you what that means. So we'll jump into a demo. On the left side of my screen, and I saw the comment in the chat about size, so I've tried to blow things up as much as possible. I'm using a fairly large font size in HMS, and then on the left, hopefully you can see that. But on the left side of my screen, I have a demo that I set up of this new feature. So if you don't have that URL, I'm sure somebody can help me out by pasting that in the chat, and you can get to this demo, and we can supply it at the end. I'm going to walk through this as a means to demonstrate this feature. One thing that I should say is in this demo, I'm going to demo gridded deficit and constant losses. This new global editor approach applies to all of the methods you see here. So that includes gridded simple canopy surface, gridded SES loss, green amp loss, soil moisture counting loss. It's been applied throughout. All right. So this project that I have, you can assume that it was migrated from a prior version and its current state. And it uses gridded deficit and constant losses. So I've selected one of the subbasins in the model. If I go to the loss tab, this looks a little bit different. Like I said, in the past, you could only ever initialize from a state grid. Now the initialization type is an option. So you see the initial deficit type, we're initializing from a state grid as opposed to specified values. And that pattern repeats itself for each of the 4 parameters in gridded deficit constant. So we have initial deficit, max deficit, constant rate, percent impervious, each of those initialized from a state grid. That's what it looks like in the component editor. Now let's jump to the globals, which is where most of these changes have taken place. So I've selected my basin, parameters loss, gridded deficit constant to open up a global editor. And now you see the global editor. The first thing you should notice is there's now 2 tabs on this global. there's a subbasins tab and a grid cells tab. So on the subbasins tab, there are subbasin level parameterizations, the kinds of things that you would parameterize at a subbasin level. So that is, how are you initializing a particular variable and then a scale factor applied to it. So those are the things that you see on the subbasin level parameterization of the global. Well, let's move to the grid cells. So this is the like I said, you can now see values on a grid cell by grid cell basis. So what I did, I just went to the grid cells tab and then I can see parameterizations for each grid cell. So this model is currently set up to initialize state from a grid. So the values that you see in this table are being sampled from a raster, which I believe happens to be HEC DSS format. It could be GeoTF. Either way, we have a generalized data reader now, so it doesn't really matter. We're just reading these values from a raster, and they're showing in this table. So these are the values that are sampled for each grid cell. Now, the nice thing about this is that one of the problems with gridded modeling in the past is often somebody would run a simulation run, they would get an error about a particular grid cell and something that was wrong with it, and not really have good visibility into what the value was or why it was bad. And what this introduces is ability to see an actual value. So let's just say for some reason, I got an error that said index I 711, index J 1061, subbase in each branch, Mahoney Creek, say the constant rate was bad. I could actually see it in this table. So that's why it's it helps you troubleshoot your own models. And it helps me troubleshoot your models. If you say, I can't figure this out, well, this is just another aid or tool that I can use to look into what's going wrong. So in this case, we're sampling all of these values from rasters. And what I said earlier is there's a new approach that we can use called specified values, where I don't have to sample these from rasters, I can specify them directly. So I'm going to illustrate that. Let me just change the initialization type for all of my model parameters. And I'll hit apply here. So I've changed that type. Now, if I go back to the grid cells tab, these entries are empty, but look, they're now editable. So I can put anything I want in here. Now, a way to put fairly intelligent values rather than just, I mean, I can certainly parameterize these individually, which seems a bit burdensome, but I can apply our expression calculator, which has been in the program for some time now. And what I can do with that is I can sample from a raster. So we're doing the same exact raster sampling, but like I was saying, we're only going to do this once now. So not every time I compute or every time I open this editor sampling. Let's go ahead and just do this one time. So the field, initial deficit, and the grid I want to sample from, initial deficit. So I can just run calculate on that. And I've added values for every single grid cell. Now I'll repeat that process. Let's go ahead and do that for constant rate. Same thing. Let's do that for max deficit. And finally, percent impervious. Let's change this. All right. So one thing I'll tell you that you can't see is that each of these rasters that I have in the program actually uses a different projection and grid cell size. And that was just something we did for testing purposes. Mike helped me out with that by generating some rasters from Sergo. And just as a way to test this, I said, use any grid cell size, you use different ones for all of them, and then use different projections. And I just want to verify that we can sample values. So traditionally, when you did gridded modeling in HMS, some of you might not know this, but you had to have it, like I'm using a structured discretization of 2000 meters and a projection of SHG in this model, which you can see here in my basin illustration. In the past, all of your state grids had to be that exact same grid cell size and the same projection. So I'll say in terms of sampling the raster, that's no longer a requirement. Also, if I were to use rasters to initialize my state, that is no longer a requirement. So we've done a lot to get away from that rigidity and how the project's set up. All right, so I just showed how I can sample values. So I can hit apply. And we're no longer reading these from rasters. So where are we storing these? Let me show you that real quick. So every HMS project or basin model has a backing geodatabase file, and it's a SQLite file. So it'll have the same exact name as the .basin file, but the extension will be SQLite. Let me browse to the one. My project is ctemp honks. And then, like I said, SQLite is the extension we're looking for. So let me go ahead and open that. And then if I go to the Browse Data tab and I select Gridded Deficit Constant, I should stop short here and say that I'm using the database browser for SQLite program to crack that SQLite file open and take a look inside. And this is just where even things like these shapes that you see in the graphic here, these are stored in this geodatabase. So this table of gridded deficit constant parameter values is stored in this geodatabase now. So I've sampled values from the rasters one time, and I can use those for simulations. So I can run a simulation with those values. That should all work fine. Now, what this sets up is that now I can do very granular calibrations. In the past, your calibrations were limited to scale factors at the sub-basin level, which you can still do. So if I wanted to apply a scale factor of 1.1 here, I can do that and I can click compute. But what we're doing if we're on this grid cell by grid cell parameterization, what we're setting up is the ability to change just the grid cells that we're interested in. So if I had good reason to believe that these particular grid cells sat over a particular surface soil texture, then I could change them as I saw fit. So I could say multiply these by a constant. I want to multiply them by 1.5. And I've just changed just a small subset of those grid cells. And I can compute on that. So I'll say the ability to both visualize and edit on a grid cell by grid cell basis is incredibly powerful. And I think some of that power is yet to be untapped as we develop more geospatial tools to make these kinds of edits and changes and support those changes. But the real power in what we see here, or one of the biggest advantages, is we maintain the spatial heterogeneity of our basin. So we can, we have these rasters that are based on soil properties, and on a grid cell by grid cell basis, we can maintain that heterogeneity and still perform a calibration by adjusting the values. All right, so I showed the global. Let me just show one more thing. Let's go back to the component editor. So let me select a subbasin. I'll go to the component editor. What does that look like now that I'm using the specified values initialization type? Well, I can see a field that shows me where those values are stored, which happens to be the geodatabase file that we've opened over here. And then I also have my scale factors. But if I want to go back and make grid cell by grid cell edits, this button here, it's kind of an old school way to say edit, I guess, is the icon. So if I click that, that will just open my global back up and allow me to make edits to the grid cell values, because it wouldn't really make sense to try and put this big table that you see here in this component editor. So we just, from the component editor, launch the global again. So that's how that works. And I launched it from the East Branch Mahoning Creek subbasin. So we actually just make that selection initially. It's only East Branch Mahoning Creek that's been selected. But I can also filter this. I can go back to no filter, which would open up all the subbasins for editing. All right, so that's that. Let me jump to my summary slide. Well, struggling to find my summary slide. So Mike, you're on deck. Mike's coming up next. Let me just scroll down in this tutorial to my summary section. So I'll just recap. Being able to see and parameterize the values on a grid cell by grid cell basis, incredibly powerful. This facilitates parameterizing and troubleshooting gridded methods. And then the specified values, it enables granular editing. So that is something that you would not get if you were using state grids to initialize. All right, with that, I'll kick it over to Mike, who's going to show a little bit more advanced application of these cool new tools.
Sweet. Thank you, Tommy. Before I do that, I do want to recap what you guys just saw, because I would be remiss if I didn't take a second to just talk about this for a second. I started my career at HEC, or at HEC, in USACE before I even came to HEC, using fully distributed gridded modeling. I found out very quickly that is a really hard thing to do. It's great to think of like, oh man, I want to use all of this information possible out there that is available, like GSurgo or NLCD data, whatever else. And I want to, instead using big subbasins that are maybe hundreds of square miles, I'm going to use individual grid cells that are postage stamp size. That's great until you find out, like, even from that simple model that Tommy showed there, with 3 subbasins that encompasses maybe like 100 or so square miles, there are 150 2-kilometer grid cells, something like that, 200 grid cells. That's a lot more data to parameterize, to provide. And that's really difficult to modify in an intelligent way to calibrate. The tools that Tommy just showed you, the advancements that he just showed you, bring that all to the forefront, and they are all at your fingertips now to use. So please take a second to think about this, of how much of an advancement that is and what type of things you can now do. For instance, a lot of times I would just take GSurgo data and I would dumb it way down to a simplified single value for one subbasin. I just took all the sand, all the clay, all the silt, whatever else, and I lumped it all together into a single representative value. And that made me feel bad. You don't have to do that now. Every single grid cell gets its own parameterization, which is always what was happening behind the scenes. We were actually doing these computations behind the scenes on each individual grid cell, but now you can actually see what those parameter values are, and you can still very efficiently and very quickly calibrate and modify those parameters. So that is huge. Game changer in my mind. Very excited for that one. All right, let me talk quickly about a modification that has now been realized because of the gridded parameterization framework that Tommy has added and others have added. Now, certain things that you can make use of within the transform world. Because if you know me, I love hydrograph theory, I love transform methods, talking about them all day, every day. HMS has 6 different transform, or we have 8 different transform methods, but 6 of them are hydrograph theory applications. In the past, all you could do with those was use the discretization method of none or structured, which is those postage stamp, say 2-kilometer grid cells, which are pretty standard. Hint, we make changes to that. We also have this other method, the 2D diffusion wave transform method, that required the use of an unstructured discretization, which could still be rigid and still be Cartesian for sure, but it doesn't have to be. How can we marry these 2 concepts together to get the best of both worlds? Well, now you can do that with this gridded parameterization updates. Oh, and I'm not going to talk too much about the 2D diffusion wave transform method. We have previous presentations that are related to that. If you guys are interested, check out that link that I put down there for a YouTube video. But say, for instance, on the right-hand side, I got this really cool mesh that I generated from RAS 2025, right? I got my triangles, I got my quads where I really want water to be flowing in a channel. I really expect it to be along those flow lines. I have my faces oriented perpendicular to that. It's great. I want to use that stuff as much as possible. We can bring that into HMS. We can actually do cool stuff with this that are very useful for dam and levee safety applications. So what does ModClark do? ModClark is a special hydrograph transform method that essentially figures out how fast it'll take for water to flow from one location to another. We're not actually routing water from one grid cell to another, but we are constructing a very intelligent time area histogram, which is actually the math that's going on behind the scenes. We start with this concept of an isochrone. Every single one of these lines that you see along here represents an equal travel time, or an equal travel time for each one of these locations. So if a drop of water fell here, it would take 10 hours to flow to the outlet. If a drop of water fell here, it would take 10 hours to flow to the outlet, so on and so forth. From that, we actually parameterize each one of these grid cells, which is our standard, SHD 2-kilometer, whatever resolution in here. We dumb down that information quite a bit to generate this kind of rigid time area histogram, this blue line behind here. What if I used this much more intelligent representation of discretization for the overland surface. I can get this much more intelligent and smooth shape for my time area histogram to make a better informed decision on how water actually moves throughout the watershed. So I'm going to do this super quick. So now we're running up against our 15-minute rule of thumb for questions and everything. I saw Paige's question from before. I want to show you guys real quick. How do you increase the font size here? So if you go to Tools, Program Settings, you pull up this menu here that you can increase your font size. I think default is 12. You can go all the way up to 14. You can make the font a whole lot bigger. It's tough when we're actually on these different size monitors, right? Not everybody has the exact same resolution in here. I'm sorry if you guys are now leaning way forward, looking really, really close in here. Whatever. Just hang with me for a second. I'm going to show you the pictures and keep it cool. All right, so I have my standard setup here where I have SHD 2-kilometer grid cells. That's great. I've always been able to do that using unihydrograph theory. I can compute all great. I'm going to apply precipitation to each one of these grid cells. I'm going to compute losses to every single one of those grid cells as well. And then I'm going to take every single excess precipitation time series that I generate from that. I'm going to use unihydrograph theory to route it to the outlet, come up with a direct runoff hydrograph, combining base flow, blah, 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 so on and so forth. Now I want to do something a little bit better. I'm going to right click to that, create a copy. Now I'm going to call this 2D diff wave. I can spell. And now I want to import a more intelligent discretization. I'm going to go to File, Import, HEC-RAS, HDF file. I'm going to choose the HDF file that I want to use, which is this guy here. I want to apply it to this 2D basin model. I'm going to apply it to the sub-basin within this 2D basin model. It has 4,500 grid cells. There's one boundary condition. Great. I want to do that. Now that I've actually imported this, I get all my triangles. I get my quads. Everything is looking like I want it to look. I'm going to expand this out because I got to provide a little bit more parameterization to it. I have one way for water to leave this mesh. I'm going to apply a whole bunch of precip on the top. I have one way for this water to leave this mesh called normal depth down here. It is a normal depth boundary condition. I'm going to connect that to my outlet sink, and I'm going to say every ounce of base flow that is generated goes to this 2D connection. I also want to make it a little bit faster to run, so I'm going to change this from adaptive time step to fixed time step, and I'm going to use 4 cores instead of 1, just because my machine has that. I can create a new simulation, and I'll call this 2D diff wave. I'm going to select that simulation. I'm going to change the basin model from what it was before. I'm going to say, yeah, just because I can. I'm going to turn on spatial results, and now I can compute. Great, great, great. We've all seen this before. When I click compute, I'm actually using the exact same solver that the latest and greatest version of RAS is using. So thank the RAS team for making all these enhancements along the way to give us faster compute speed, more stability enhancements, new computational options, things like that. It's great. We get all the benefit of that for free, which is awesome. So thank you guys for doing that. You actually access all of that information when you use the 2D diffusion wave transform method in here. Cool, cool. I'm gonna let this go. I'm doing a lot more computations as well. So you gotta let this one ride for a second. It's not as fast as unihydrograph theory because we're doing a whole bunch more with it. And you get some additional outputs and options that comes along with that. You guys have all seen this before. If you want a whole lot more discussion about it, please go check out that previous video that I linked in here as well. But again, I use the 2D diffusion wave transform here as well. Let me do this cool new thing with it as well. So I'm going to say 2D diffusion wave. Instead of that, I'm going to call this unihydrograph mod Clark. I would like to keep this discretization, triangles, quads, whatever you want, whatever worked before. I'm going to keep that exact same thing. But instead of that, I want to use mod Clark. And instead of deficit and constant, I want to use gridded deficit and constant. Now I can get some really cool stuff that comes along with that too. In particular, I want to do the specified values awesomeness that Tommy talked about before. I can go into the global editors and I can access every single one of these grid cells. The thing that's going to look different in here is there is no J that goes along with this. That's a convention that we bring along from structured discretization, where there's an IJ for everything that goes along here. Now we just have individual I. This is like just a single index that goes along. Again, we have 4,500 grid cells. We start with 0. Yep, we start with 0. So there's 4,585 grid cells that goes along with this. I can specify the initial deficit, maximum deficit, constant rate, impervious area, whatever I want, For the specific method, I can also use the calculator to sample from GeoTIFF, ASCII, DSS files behind the scenes and parameterize all of these guys. And I can calibrate as well to come back on the subbasins tab to use my scale factors. I can modify individual grid cells if I want to. This sets us up really nicely for other things like index maps and HRUs, which are great too. But we don't need to do anything crazy for right now. I just want to turn this back to simple, regular old deficit and constant. And for transform, now I'm using mod Clark. I'm going to give it a time of concentration and storage coefficient. I'm going to create a computation, or create a compute. Instead of 2D diffusion wave, I'm going to sell hydrograph mod Clark. I'm going to call this guy that. Turn on spatial results, yeah. And now I want to compute that. All right, and now what I did was I actually computed a much more intelligent time area histogram for every single one of these grid cells again. Instead of using the huge blocks that are 2 kilometers by 2 kilometers, now I'm using teeny tiny triangles and quadrilaterals in here that better represent my expected movement of water on the overland surface to make a better informed estimate of how water actually moves throughout here. Now I can do really cool things, like I can compare direct runoff hydrographs that are computed using the SHG 2 kilometer grid cells to the more intelligent unstructured mesh that I just used. So the dashed blue line that I'm showing right here is better because I discretized the overland surface in a more intelligent way. I didn't take these broad brush sledgehammer approaches to using computing a time area histogram. I can also do another really cool comparison where I'm going to expand 2D diffusion wave, and now I'm going to pull up the equivalent of the direct runoff hydrograph from the 2D diffusion wave transform. It's called surface flow, that time series. I'm going to compare these two over here. And the differences between them are solely due to the transform method. The one that I was showing you before is not due to the transform method at all. It's due to the discretization, how I discretized the overland surface. Now these differences are solely due to the transform method that was selected in here, right? We have a workflow that we have talked about in the past to utilize a much more intelligent way of modifying these parameters in time. So as it rains harder, we would expect time of concentration and storage coefficient to decrease, or at least change, right? We've talked about ways to come up with these concentration and storage curves. One thing that we recommend is like, hey, why don't you just build a 2D model and simulate the movement of water on the overland plane, and then compare and contrast what you come up with using hydrograph theory to that to come up with these intelligent these time area histogram modifications or concentration and storage coefficients, right? Now we can do a better job of that method because we have these gridded parameterization modifications that Tommy has made. Now we can mix and match discretization, transform methods, loss, everything like that is at your fingertips. Very, very cool stuff. All right, finish this up really quick. I cannot specify, or I cannot say this with any more emphasis. This is a big deal. I have a feeling that this will get a whole lot of usage in the future. I will specifically be using this quite a bit because I can now sample from a raster to start with to give me my intelligent estimates of parameters for every single grid cell, and I can very quickly and efficiently modify them to calibrate many, many, many grid cells, many, many subbasins to achieve a desired level of performance at a specific location. Because of all these options that have been added in here. If you were used to the state grids in the past with scale factors, you can still do that. You can even twist it and make it better than it was in the past. We have some more stuff coming. Index maps and HRUs are an exciting new avenue we would like to add within HMS. If you're interested in that, please reach out, contact us, let us know. All right, I'll kick it back over to Lauren.
All right, thanks, Mike. So before we get into questions, just wanted to give a quick thank you to our funding partners for these features. We have the SWIM's National Implementation Program, as well as Ensemble's R&D program, and then finally our Science and Engineering Technology, or SET program, that allows us to do a lot of maintenance on a continuous basis. And then next slide, just a quick plug for our Confluence page, our documentation, a lot of great information in the user's manual, tech reference manual, tutorials and guides. And then finally, all of you should be on the email list because you got this, but encourage your friends. If not, they can subscribe to our email list, get information about future releases, as well as future quarterly webinars. So with that, we will take the last 5 or 6 minutes to go through any questions in the chat. You guys can keep putting them in. So I'll just read them off as we go, the ones that haven't been answered yet. So Ryan Johnson asked, can direct runoff route it from one cell into a, oh, sorry. Tom already took care of that. All right, next question.
I mean, you could, Mike, do you want to talk to that? I think I got that right.
So we did have that at one point in time. We turned that option off because we wanted to actually produce similar results to what we were getting with HEC RAS, to just take excess precipitation from precipitation that was applied to each individual grid cell and let it go. We do have the option of turning that back on. We were not getting what we thought were appropriate answers at that specific time. We do have that option. That is not currently how the 2D diffusion wave transform works. It did at one point in time, but it does not anymore. And then question from Merari was along that same line, estimating infiltration while using Mod Clark. We do not route water from one grid cell to another. That is 2D diffusion wave, right? Mod Clark just discretizes each individual subbasin to come up with an intelligent time area histogram. Each individual grid cell does get precipitation, and excess precipitation is computed for each individual grid cell, but all the individual pieces and parcels that are computed from each one of those grid cells get summed back together to compute a single direct runoff hydrograph called convolution. That get at your questions, Merari? We do not do infiltration twice.
I guess
Just
everyone's
once.
on mute, so you gotta please post in the chat.
Almost. Close. If you guys want to talk, we'll talk for hours with you. If you would like to talk about unihydrograph theory and how this works, hit me up. We can talk more about it. Yeah. I'm not allowed to talk about it at home, so I gotta take it out on you guys.
Any other questions?
No one asked when the next release will be yet. I think most of these features are actually on the street, if that's how you want to put it, in 4.13. So feel free to
There it is.
yeah, thanks, Avatal. That's you're supposed to start there. There we go. When will the next release be? That's always the hot question. So all of these features that you've seen should be in the 4.13 betas that are out there, so you can pick them up and play with them. And then I think 4.13 should be in a final state. We'll say tentatively say Q1, well, Q1 of the calendar year, Q2 of our fiscal year. So sometime between January and March of next year would be our goal. We'll see if we hit that or not. Size of the rasters, not explicitly, although I think everyone should know just the more data you're trying to handle, the more performance can be impacted. I haven't seen any terrible impacts to anything you've seen today as far as like throwing big rasters at it yet, but I haven't tested the domain of what's possible either. So feel free to throw something big at it, and if you break it, I'll either tell you your data's too big, or I'll make an improvement to fix it. I'll have to make the determination when I see it. That's how performance kind of works. So yeah, background imagery that and DEM download, those are both things we've talked about. So if those are of interest to you and you have some sort of funding source to help us see that through, let us know. We'd love to add those to the program. Mike, are you tracking Ryan's ability to turn on continuous infiltration?
Yes, I have aimed this out quite a bit. Of most of the complexities come about not because of the model code or the actual compute stuff behind the scenes, but the user interface that goes along with that, and not making bad choices when it comes to, well, we took this many options, now we made it this big. So with funding, all things are possible. I'll say that. If there is a willing partner that comes along and would like to partner with us through design, implementation, and testing, for sure. However, not as of right now. We will not turn that back on. It's possible though.
Mirza has a good question about geometry editing tools. Yeah, we'll see where that goes. Right now, it's kind of hard for us to start adding those because I'd say the RAS team is adding and modifying those quickly, and we're kind of just piggybacking off of them for 2D diffusion wave. So we're following their lead, and as long as that's highly dynamic as it currently is, I wouldn't see us jumping in and trying to add those tools, although it's a very good idea. So currently, if you're editing those geometries, it has to be done in RasMapper. We'll see what the future holds.
Okay. Well, we have hit our hour. So I want to thank everyone again for attending the webinar. If we didn't get to your question, or maybe if you think of a question later on, please feel free to email us for a follow-up. Just another reminder that this video will be on the webinar page shortly. You should have the link in the invite that was sent out to all of you. And then as well as the rest of our webinars are there as well. So again, thank you all for attending and have a good rest of your day.
Thank you.